Yeah.
What's going on, Michael?
So, yeah, I mean, your format function should be basically just deleting every file in that case.
Yeah.
I wonder if I could
Project 2 come on.
try something.
Not as good as I was hoping by the point, but.
Whoa. I like the Stairway to Infinity thing on the video camera. Oh, what I was wondering, see, I want to show everybody the, not just show the, give away the answers, but actually explain the questions on this thing. And I'm wondering, I always put it on the projector and it looks terrible. Maybe this little webcam will give me an even fuzzier one. Let's try this.
Whoever was watching this on YouTube, if it was recording, would be sick.
Yeah, is he sick by now? Yeah.
Good morning.
Good morning.
It's still dark.
Good afternoon.
Yeah, it is.
It's morning.
It's
You know what?
morning.
Don't talk to me, Colin.
Why?
You got 100 on the physics exam.
Well, I'm sorry for accidentally doing a good job.
Accidentally.
Yes, accidentally.
All right. I'm just gonna do this.
I don't even know how you got
Right? How do you
You just wrote all the right answers and you can't tell what happened. It's for some reason.
I don't remember what was on the exam.
curve? Like I was really hoping for a curved exam, but no. Thanks to Kyle.
Well, Gus, maybe you could study better and you would get.
I could.
Maybe you could have studied better.
That would be an option, I believe.
I have some extra trash cans and things if you need to dispose of him.
This what? Hold on. What?
Conspiring against you. Just go.
I don't like where this conversation is going.
You shouldn't. Good, Grandma Dirt bottle. Okay, that works. I need to get the. I think I will use the Elmo. I don't like the Elmo very much, but
Why do they call it that?
because it says Elmo.
Elmo's well.
It probably stands for something.
Yeah.
Or not, I don't know.
It's not just like they call it that. I mean, it's got it written on it in like professional lettering and things, you know.
Is it like Tickle Me Elmo? When you light it on fire, it laughs at you creepily?
You don't know.
You've done
Really
that?
funny. I've never done that before.
There's YouTube videos of it.
It just laughs while it's burning.
Yes.
That's how you should always
really
approach life.
creepily too.
Just laugh while
Well, it's probably
everything's on
just
fire.
distorting the speaker.
And then it looks like the tiniest Terminator when you're done.
I'll do that.
I see the video where it turns into the Terminator, it kills everybody after the skin's burned off, hiding there the whole time.
That's kind of like.
You know, that's what they should do in the next term. They made like 4 Terminator movies, and I've only seen the first 2, but I'm already planning the 5th one now. He comes in as a Tickle Me Elmo. And when did this come out? 90s or something?
Tickle Me Elmo?
Yeah.
Like 90s, yeah.
Yeah. It's one more attempt to kill John Connor.
I've seen the first, second, and fourth movies. Never seen the third.
I've only seen the original 3.
I think the third is Redemption or whatever. It's set in the far future.
Oh no, that's the fourth. No, the third is in like present day or something.
Yeah.
It's like an adult.
Like a
when
different
they launched
Terminator,
the
which
Luke,
like they
or
now do.
the launch the nukes at the end. That one was terrible, except for the female Terminator was incredibly attractive.
I
Sounds like
like
she would
the,
have killed you.
I like the relationship.
Yeah, most likely. And then again, my name's not John Connor.
Yeah, that's true. My name. Oh, I should start handing these things back.
How was the average on the test?
How's the average? I didn't bother computing the average. I never do.
Did you curve it?
No, I didn't curve
No,
it.
Kyle.
The median was a 74.
What, is it that hard? Damn.
That was
Well,
about how the physics test was. Like 77.
Except for some people.
What?
okay. Oh, apparently I was recording. Probably through the whole time I was busy moving the webcam everywhere. Oh well, whatever. Oh well, this yeah went okay. Like I said, median was 74, and so that's I don't know, it's not that bad. This class, the big part of the class is really the projects anyway, so that's fine. Okay. Anyway, there's a table in the way here. There used to be a table in the way.
Thanks for putting prologue code on my exam, by the way.
Oh yeah, I wasn't sure if that's what you were getting at there or not, but
No, I mean, I just put Kyle's shoe down for makes Kyle's shoes, implies is Kyle's shoe.
well, yeah, you seem to be stating it both were true, and so.
I think my great-great-great-grandfather was a shoemaker or something.
Maybe back into history of things.
My mom's side of the family was Danish royalty or something along in the 1800s.
My last name is Juan, apparently means fierce. Okay, this one, number one, is almost a little bit of a trick question. Not really a trick question, but it can send you the wrong way. It says user programs run at privilege level 3, and which level do programs run by root, the root user, run at? Well, root's a user, and they run at level 3, like the rest of the users. So remember when we were talking about the privilege separation, basically this is coming back to the Intel diagram. Well, it's actually common to more than just Intel, where we say, wait for the web browser. Okay, that's all spelled badly. There we go. Okay, so I got different privilege levels here, and applications get level 3. Well, application here means anything outside the kernel. And the device drivers, of course, have to have a higher level, and the kernel gets level 0. But the only way to get back to level 0 after the kernel initialization routines is to make a system call. And when you make a system call, code gets run at level 0. The other way is a device interrupt of some sort, hardware thing. And those will also give you something that runs at level 0 in order to respond to the interrupt. Okay, but without some kind of interrupt, you're not going to have a level 0 code run. And so if root runs a program, it runs at level 3, just like every other user. Okay, video. This one over here about kernel modules and what they're commonly used for. Well, there's so web browsers, is the program used to browse the internet, so no way. Bootloader loads the kernel, so it predates the kernel here, so no way. Memory manager. It's possible to write a memory manager in a kernel module, but this is not something that it is commonly used for. And so can't do that. System calls. It's technically possible to add one, again, as a kernel module, but it's not something that they're commonly used for. So anyway. The one we're used for all the time is device drivers. And this is my example, kind of the continuing example where we talked about this stuff. So there you go. Okay. So then this one over here, about the bootloader. This one confused people. A lot of people got this one wrong. Nobody selected option D. I was surprised there. Well, I wasn't surprised. But I would have been amused if somebody had, I guess. Anyway, so the bootloader. It's stored on the boot disk, and that can be a floppy in the case of Linux 0.11, or like a CD or USB drive or whatever, hard drive. And so let's see, loads the GUI. No, it doesn't do that. The graphical user interface is loaded much later. We haven't talked about the GUI at all because on a Unix-style system, it mostly is just user space stuff, really. And this is pretty common, actually, for how they go. At some point, maybe we'll talk about the lower level display system and how you actually build one of these things in user space, but it doesn't do that. Okay, BIOS loads it into memory. And remember, there's a specific address that loads it at. And I can't remember at the moment the exact address of it, but it loads it into a predetermined spot and starts running it. And The main thing that the bootloader does is load the rest of the kernel. So it doesn't go find all the device drivers. The kernel will do that later. And yeah, it doesn't do the other things. Oh, paging. So paging, this one, a lot of people got it right. It's memory management. But the occasional person ended up picking one of my scrolling or keyboard options. And those look tempting because, you know, you have pages of text and so yeah. But no, this is a memory term. And so paging, remember, is when you take your memory and it's divided into spots. And so when you have some kind of a program run, you give it its own memory space. That's probably bigger than the physical memory on a computer. And so then you got some kind of mapping here, where the program stores something and you store it somewhere in main memory. And in fact, you can even store it off on the hard drive. And that's fine too. All right, so that's paging.
Well, it's not completely fine, because if you store it on the hard drive, I think it takes longer for it to...
Oh yeah, yeah, a lot longer. Yeah.
It'll still run, but it'll be snail page.
Yeah, hard drive access for a spinning type drive is approximately 1,000,000 times slower than main memory. And for a solid state drive, it's approximately 1,000 times slower.
Huh. One time, just for fun, I decided to write a program on my computer, a C program, that I think it just ran in and allocated like 2 million bubbles or something. And it didn't actually like free up the memory, it just used up all the memory. And my computer ran really slowly for the entire day, even after I restarted it. It was really fun.
Weird. I'm surprised restarting didn't fix that one.
I don't know, well, it just seemed like it was running really sluggish after I restarted it.
Okay.
It ran especially sluggish after I told the program.
Did it have any enormous page file sitting around?
I don't know, I didn't see anything.
Okay. Because on a Windows system, if you do that, you can end up running out of hard drive space because it'll make a bigger and bigger page file. On a Linux system, it has a separate partition, and you can fill up the partition and crash it. It's like a separate swap partition. Both approaches have their own particular disadvantages.
I just wrote it just to see what would happen.
Yeah.
My
Yeah.
computer went slow and it said the program crashed or something because it ran out of memory.
Yeah. Yeah, I would eventually do that. Because eventually the program is going to call malloc or try and declare a local variable or whatever, and the operating system is going to say, no, you can't. Okay, stuff found in the operating system kernel. So there's, yeah, following is not found. Okay, so the device drivers, those are in the kernel. Even if they start out as kernel module, they go into kernel, and you need some of them in the kernel anyway to drive basic stuff like the hard drive and whatnot. So those are going to be in operating system kernel. File system drivers, yeah, they're going to be in there. They can be made a module or not, but they're going to be there. Network interface support, same thing. Memory management, yeah, that's in the kernel. It's probably not even a module. And the bootloader. Well, the bootloader loads the kernel, so it can't be inside the kernel. It it loads the kernel. So that's not happens first. Okay, these ones, block devices. So block device is a device where you can access parts of it kind of randomly. Think a device with random access to it. Something where instead of just giving like a sequence of input, you can say, I want this particular bit of the device's memory. So that webcam over there under the phone, that would be a character device. It's feeding me a stream of data. And the keyboard and mouse, they do a stream of data. Scanner, like for a document, same thing, stream of data. Network card, stream of data. Memory card is the one that's different. It has a memory space where you access different parts of the memory space kind of at random. And so that's a block device, presents a block of memory. Okay, and then this whole one here, which doesn't use B trees. Last time I actually asked with ext2 and it was esoteric and everybody hated the question. So this time I put file allocation table on there, and I think just about everybody put that on there because file allocation table doesn't use B trees. XFS is Silicon Graphics file system. It's used a lot in Linux. I think iSoftware might be running it. B-treeFS is a newer B-tree file system. Last I looked, it wasn't that well debugged, so I haven't used it. NTFS is used for Windows, and RiserFS was one of the pioneers in this, putting everything into B-tree kind of file system until the creator of it ran into legal troubles of his own making. So there you go. Okay, he's infamous for that now. He had a great reputation in like software development, and now that's all people remember him for. Okay, operating systems. What are they generally written in? And the generally here is kind of important. If you really wanted to, you could probably write an operating system in just about anything. It would be really hard in certain languages, like Python, for example, because first of all, the Python interpreter is going to have to be written in something. The standard Python interpreter is written in C. PyPy is a Python just-in-time compiler that I believe is written in Python. But anyway. Okay, so usually C and assembly, that's what we've been looking through this whole time. C and C#, I mean, you could, well, C# requires a just-in-time compiler, which is going to have to be written in C. You don't want just-in-time code in your operating system, that'd be a mess. Java uses a Java virtual machine, and maybe you could write an operating system for the JVM, and that might be a cool project. I never heard of anybody doing it, but JVM's a machine, should have an operating system. Python and C, no. C++. This is the only other like viable alternative on this one. And I mentioned before, Windows and Linux and OS X are written in C. And so it's not C++, but you could write an operating system in C++. There's no reason that wouldn't be a perfectly fine choice. And in fact, if somebody was starting a brand new operating system today, they might even choose it.
Yeah, I actually would want to try writing one in Python. I'd call it Pyos, I think.
Oh, yeah.
Pyos.
Yeah. Oh, so this multiple choice page. I've always put a multiple choice page, and this is usually the page I take the most points off of. And you guys have been around the block a few times, so you're not quite get disenchanted with the whole multiple choice question. People are in my 100 level classes. It's like, is it multiple choice? Is it multiple choice? And they're like, the first page is multiple choice, and they're like, oh, good. And they don't realize that multiple choice means I can lead them to their doom.
Yeah. Aside from multiple choice, it's my specialty.
I don't know. Like this one up here, it's like, okay, which level to root? Oh, root, very special. Okay, well, that's not a user, but it is a user. I feel almost a little bad about that question. I don't know.
Man, didn't trip me up. None of them did.
Oh, really?
I think I passed it.
Oh, cool.
Short answer are my weakness.
Yeah, the short answer ones, people can make up stuff, and sometimes it'll be right. I've had students before that would like make up stuff and be right most of the time, and sometimes people make it up, and it's like, well, that'd be a pretty good idea, but sorry, it's not done. That works too. Okay, well, it gets partial credit at least. It was like, hey, look, you made a solution. All right, well, anyway, what is a void star type? And when do you use it instead of pointer to a specific type? Well, on this one, you use a void star if you're going to pass a pointer, but the exact type of that pointer is either hard to express, and this can happen. For example, if it's a function, it takes a pointer to a function that can potentially be itself, then you got a crazy mess. And using a void star can oftentimes clarify the whole thing. So that's one reason. Other reason for a void star is if you're just not sure what the type is going to be. And so I showed pthreads, for example, on here. Let me swap back to the video. I might not even go back to the test for a little while. Oh, that's what I wanted. This one. So if we go and look at pthread create, pthread goes and starts a new thread, and it takes a function pointer. That's the function it's going to start, and it doesn't use a void star for this right here. And this is not a void star. This is a pointer to a function. It takes a void star and returns a void star. This is quite a different thing. But this void star here, this is the argument that's given to this function. It takes a void star, and the reason is when they're writing a pthread library, they don't know what function you're going to pass in. It's got to support all functions that you might want to do that with. And so for any data structure that you might want to pass to your function, you can take that data structure and put it in memory and get the address of it. And so the void star makes a way to pass that address And then inside your function, you can take care of casting it to whatever you need to cast it to make it comprehensible. And so that's another good use of a void star. Okay, that's what it's used for, and that's what it's used in. They're kind of the same question in a way. I feel like I should have worded that differently. To either have two things that are different or condense it down into one. But anyway, for the most part, it worked fine. There's the occasion when somebody answered what it was used for, and not like when you use it instead of something else. But yeah, for the most part, they're kind of joined. Oh yes, the next one. The next one there, question 10. Seeing you have this in front of you, I'm not going to switch back. Describe the role of file system in an operating system, and what characteristics do they all have, and how do they allow the operating system to function on multiple hardware types? Okay, there is a genuinely different question at the end there. Okay, so the file system stores files, obviously, but as far as what's common to it, well, they all have a way to save files, a way to find files, a way to get files back, a way to, no they don't. A lot of them have a way to delete files. Not all of them. CDs, optical discs. You can't delete stuff. So most of them have a way to delete files. Most of them have some notion of permissions, although not all of them. FAT and ISO 9660, the CD file system, don't. So really, the ones that are common to all are you can put files on them and find the files. And that's really the main point of commonality there. Okay, most people listed a bunch of stuff that's common to most file systems, which is absolutely fine. There's usually some kind of weird exception to about any rule. And so, if you said you can create and delete files, then yeah, it's fine. Okay, and then finally, this last part. This is the one where people are missing it. How does the file system help the operating system to function on multiple hardware types? Well, you've been writing one, and we have a number of sectors and a number of tracks and such for this hard drive. Well, those are defined as constants at the top of the program. And so, I'm not going to do this when I test it, but I suppose for in a thorough case, it might make some sense. You should be able to change those. And say instead of that number of sectors and tracks, say we got 26 sectors and 37 tracks, and the file system should still work. And so then the test program, tester.c, it doesn't necessarily have to know about this different geometry. There has to be enough space to store everything it tried to store. This is common to file systems all over. You can't store more stuff in the file system than the device holds. But in general, it will abstract the file system down so that whatever is using the file system, like the rest of the operating system, doesn't have to be aware of the hard drive geometry, or even it's a solid state drive or something else. I don't know how their geometry is stated. In the beginning, the regular file systems were used on them, and so this solid state drive would present something to the operating system like, we got one track and we got a bazillion sectors and that's our geometry, And then the file system could do what it wanted with it. Okay, so that's how the file system helps an operating system function on multiple hardware types. It takes care of different hard drive geometry. Okay. So this next one, the file allocation table scheme. I will switch back to this. I need the video. Okay, so this one generally went pretty well. A few people, I forgot about the second part here, and some people messed up the arithmetic in one way or another. But anyway, so we got this definition of a sector. You notice this is not a file allocation table entry. This is a structure to represent a sector. And so the file allocation table is going to have a different data structure that gives a pointer to sectors that have this in it. And so this sector, it's got this definition here. It's got the next cylinder, next sector, next head. And when we see those can either be set to 0 to indicate this is all of the file is in this sector or all the rest of it, or they can indicate that you need to keep going to find the rest of the file. Okay, so you're looking at a bunch of these things on a disk, and it's got this data here, which is set up as an integer array. There's no particular reason it needs to be an integer array. It could be an array of whatever. But integer works fine, and we want to allocate some space inside the structure. That's a reasonable way to do it. And so we have sector size divided by 4, and that minus 3. Okay, so doing a little bit of math here, sector size is 1024, and if we divide that by 4, we're going to get 256. Okay, and so we take that 256 and we subtract 3. That's not really valid anymore. And we're going to get 253. And then if we take that and we want to figure out how much space is in that array, like how many bytes, we can multiply that whole thing times 4. And what we're going to get is 1012. Okay, here's another way to do that. You can look at this and say, well, we got sector size there, that's 1024. We're going to divide it by 4, so into fourths, but 4 is the size of an integer, right? And so this is like this is enough integers minus 3 to fill up the whole sector. Why 3? Well, 1, 2, 3. You know, there's 3 of them right here. And so the total of this whole area here is 3 ints, or 12 bytes. And so if we got 12 bytes there, then a sector is 1024. We're using 1012. Subtract 12 from 1024. Okay, and so you get 1012. Okay, so that's how many bytes are actually being stored in each of these sectors. Okay, thinking about the algorithm here, we asked this question using this scheme and that sector size, and assuming the file allocation table points to the beginning of the file and not like the middle or the end or something. How many disk accesses do you need to get to the end of a 1 megabyte file? Okay, and I set up the prefixes there, MIB, MIB byte, in order to emphasize that it was 2 to the 20th power bytes, as opposed to a million bytes. And I didn't hold everybody to that level of arithmetic precision on this thing, but anyway, that was the idea. And so anyway, we want to know how many disk accesses do we need for a fragmented, well, a regular one and a fragmented one. Okay, so when we start at the beginning, we're going to have to do a disk access for every single one of these structures, every sector, because we've got to look at each one to see the next one. And so, suppose this file is all stored in a row here, and we got all these sectors. And so what we're going to have to do is read that stuff at the beginning, and that's going to point to the next sector, and read the stuff in the beginning, and that's going to point to the next sector, and read that, and so on. So we're just going to have to go and read each sector in a row, basically. Okay, so what we want to know is we got our file there, and it's 2 to the 20th bytes, and then we're going to divide that by this 1012. And if you don't feel like using a calculator, you can just approximate this, 2 to the 20 over 2 to the 10, which is 2 to the 10, right? Because 2 to the 20th is 1024 times 1024. And if you write it like that, then it's all you have to do is recall grade school algebra, 1024 over 1024. Cancel, cancel, you got 1024. Okay, so that's more or less correct. It's really close. The actual one, if you go and put the one over here into a calculator, I think it comes out to 1036 point something, which is 1037, because of course it's going to leak into the last page, and so to find the end of the file, you have to make an actual disk access. So that's like I'm pretty sure that's the actual answer, if I remember right. If I'm wrong, you just put it in a calculator and have the right one.
I'm a math major, and I just totally screwed this one up. It's just pathetic. Then again, arithmetic is the hardest part of mathematics.
Okay.
I had to rather get the beginning than I second guess myself.
I try to be forgiving on the arithmetic. But okay, so there was one problem. Here are the major pitfalls on this one. First one, So this is an int data here, and this is 256. Well, it's 253 integers, and so in a few cases, folks ended up doing this one by dividing this by 253 instead, and that ends up with an answer that's way too big. And there was the occasional person who did it differently, and instead of using these, this is in integers, in units of bytes. You can also do this in units of integers, like 4 bytes units, and that works too. You got 256,000 approximately integers in the file. Okay, oh yeah, and so then the fragmentation question. Does it change the number of disk accesses if these are all over the map? If it's not cleanly going on to the next one, it's going, somewhere else. No, it didn't change anything, because you still got to access each sector, right? So it doesn't really matter if the chain follows along in the line or it goes all over the disk. It's the same number. Now somebody can make an argument based on caching and things that the disk accesses, are actually not going to require the head to move because the drive has 8 megabytes or whatever of cache in it, and so you're going to hit the hard drive cache. And if anybody said that would have been fine, but nobody said that. Yeah.
I read in the book said it only affected the seek time side. That it accessed it the same amount of times, but as it was searching, it just took longer.
Yeah. It'll send the same number of requests to the hard drive. The hard drive will just have its cache, and so when the request comes in, it doesn't bother to go seek it on the drive. It just replies from cache. Yeah. Anyway, nobody said that, but that would have been fine. Okay, so that's that one. I thought I was kind of like that question. I don't know why. Okay, this one. What features are typically part of an operating system kernel? And how do you utilize these services? Okay. Well, in terms of features, memory management, device drivers, file systems, of course, network management for network interfaces, process control. You got to be able to tell which processes are running and switch between them. And so that's the basic set there. I gave full credit even without the complete list of 5 or so. That was fine. But what I really wanted to make sure people said on this was system calls, because that's how the user space program utilizes these services. They trigger a system call on the kernel. And then the system call causes something to run in the kernel, and off you go. Okay, that question didn't go too bad. This one, on the other hand, question number 13. Nobody got question number 13 completely. Some people got parts of question 13, even big parts, but nobody got the whole thing. Okay, so there's these 3 interrupt routines, and they're called in the beginning bits of the kernel. So let's go pop over here to the computer, and I'll just show you what I'm talking about on this. Okay, put that. Oh. Okay, so we look at boot sect.s. We're looking for interrupts here. Okay, so there's an interrupt 13. And what this does is, as it comments there, read it. This reads sectors off of the disk and puts them into memory. And so that's part of the copying everything into memory stuff. Okay. And then there's one down here, 10. And 10 is used to, as he says, print some inane message. But it's used to print stuff on a display. And so between the two of those, that's the answer. These interrupts are used for copying things from the disk into memory and for displaying things.
No input at this point.
What's that?
There's no input at this point, no keyboards or anything?
Well, the keyboard's not being used, but I was talking about the 3 interrupts are used from assembly code.
Oh, okay.
Yeah, so not from the keyboard or the mouse or interrupt control or any that kind of stuff. Yeah. The last one there, 0x19. The BIOS actually calls that one itself, and so this moves the boot sector into memory. And it's not referenced right here in the assembly code, and so I don't know. I put it in there mostly as a memory thing. So we talked about interrupt 0x19 for like 15 minutes once. And so I was like, hey, maybe the number. I should put 0x18h or 0x19h, because that's how the book kept referring to it. It was putting an H after it, even though the book wasn't putting an H after other hex numbers. Okay. And I specifically didn't have to remember which number was which. I was half expecting somebody to give me a list there. Oh, this next one. This is a good one. This puzzle. I like puzzles. Sometimes. Only some days. Okay. So this you have to include it. I think 3 people got this one right. It involves a certain amount of just hopping along, being like, okay, what does what. So you have these functions here, foo and main. And so if you look at the behavior of foo here, foo takes a function called bar. Bar is down here. I wish this was focused. Maybe if I hit the focus button, it will be. Hey, there we go. Much better. Okay, so the function foo up here, it takes this pointer b, and you notice the first thing it does is make a backup copy of the contents of b, like whatever is pointed to by b. So after that, if we change what's pointed to by b, like that, it doesn't affect a. And so that it kind of changes behavior in a few ways, having this backup copy. You notice when we call bar here, at this point we're giving it the address of A. And so what it's going to change is actually A. Well, kind of. It gets more complicated because of the whole scope thing here in a minute. Okay, and here we're giving it B, the other function pointer there, and printing off A as we go. Okay. I feel like it's still not as focused as it could be. That's better. Okay, so then main down here. We got this bar function, and okay, I briefly was considering if I could have named the functions the same thing, but as a matter of fact, I could not have because I'm calling foo and giving it bar here as a parameter. Oh, anyway, so I said A to 5, B to 10, and then define this bar here that takes an int pointer called A. So at this point inside here, whenever we say A, we mean that pointer, and when we say B, we mean that other one. So this B here is tied to that B. Like those are one and the same, that B and that B. And this one here is pointer to whatever came in here. And you notice the first thing we do is set the thing at the memory address that A is pointing us to as 0. Because if we take anything minus anything, we're going to get a 0. Even if we take like -1 plus -1. No, that's not going to give us a 0, is it? Oh, minus -1. That's because I wrote the sign down wrong. Okay, -1 minus -1 is 0, right? Okay, okay. Okay, so anyway, it doesn't really matter what A is. A is going to be set to 0 at that point. So this is like saying star A equals 0. So then down here we're changing B, reducing it by 3, and returning whatever a 0 plus B. So it's basically just returning B. We've got to remember it has this effect on A. Okay. So then we call foo, we give it bar, and we give it a pointer to A. So this pointer B up here, this is actually a pointer to that A right there when this is called. And seeing it's only called once, it's kind of legitimate to just throw the arrow and say that's that. Okay, so this pointer here is given there. So the first thing we do is say A, which is a local variable. So this A here is just kind of within that area, although we're going to pass a pointer out by the end of it. And we're going to back up the value from B. Okay, so this point A there is 5. Just the same as it is down in main, because we passed this memory address up and everything. Okay, so we go ahead and print out what comes back from bar, giving it B, this pointer we have. Now, B there, we already established it's a pointer to A, and since it's a pointer to A, we're calling B and giving B A as a pointer to A. So weirdly enough, in this call to bar, A there is basically just A. Like star A is a pointer to A. Or it refers to A. Okay, so we're going to set A to 0. And this is going to have to get fixed in a minute, but there we go. Okay, so we're setting A to 0. Then we're going to take B and reduce it by 10. And I drew a little line there to keep in mind what B is. And so B is now 7. And so we're going to return 0 plus 7, which is 7, and we're going to print out a 7. And so if I start putting the output over here, okay, sorry, look, 7. Okay, and so then after that, we're going to come back to the next line over here. Remember, we zeroed out A already, but that's not going to belong. But this A right here, it's not the same as this one. This is that A right there. It's a local variable A. And so we're going to print it out. And remember, we backed up the value from here. And so this is 5. Because we took the 5 and passed it up and put it into there, and so yeah, 5. Okay. So then after this, we go ahead and call bar again, and we give it the address of A. Well, remember, A here is our local variable, and its value is 5, and we're going to pass the return value into star B, which is, as we mentioned, a reference over here to A. So we go down here, and we zero out A, which is passed in, that reference there. That's that one. It becomes 0. And then we decrease B by 3, so this now goes down to 4. And so now this is 4. You're going to say return 0 plus 4. That's 4. So we return a 4 into this pointer, which returns it to there. So A is 4 and B is 4. So then down here we print out A and B, and they're both 4. So 4, 4. Okay, that is our output. People are looking at me like, maybe it isn't, maybe it isn't. That's what you think. Okay, I did make sure. I think it's purple 2.c. Okay. Is this it? Yeah, 5 and 10. Yeah, this is the program. So here it is all written out. You have to do that. You have to type it out if you're going to put it onto a test because the printer has to know what it is. And so I went ahead and ran it. Puzzle 2.c. And there we go, 7544.
Oh, by the way, Seth, on your on the lab you had that was associated with this puzzle.
Yeah.
Yeah, on your include you forgot to put in the
stdio.h.
So actually I just wrote down, yeah, you forgot to include stdio.h, so I just wrote down first that you forgot to include that so it wouldn't compile anyway.
Oh, yeah.
And then after that I wrote, well, if you did include stdio.h, it would do that.
Was this one from the lab?
She's not going to point
That's the first part.
That was the first part? Okay, yeah.
I don't
Yeah.
think it would compile.
Yeah, you had the
I mean, that-
include. You had include, you just didn't
Yeah.
have anything else.
Good, like opening bracket, but no closing bracket either.
Oh,
It says like include
Like
arrow.
it was just like
Yeah, just so
like,
you-
Oh, like-
include less than.
like
it was something was supposed
that?
to be there, but
Yeah.
oh.
That was part of the puzzle, you guys.
Okay. Well, I'm glad you saw
I
that.
actually kind of thought for a second it was like a trick question. I really did. I was like, wait a minute.
That's- Oh, I know why. An opening thing like that, less than sign, is an opening tag in HTML.
Oh, oops.
I bet HTML
funny.
HTML'd it.
It's like that was the puzzle. What is this output? Nothing. Does not compile.
Yeah, 38. I guess I didn't look at that very well. Okay, Lab 4. Yeah, and I bet if we view source, view page source.
Yeah, you forgot it.
Yeah, it's right there. And see, it turned it purple because it's a tag.
Oops. You can put in like a code tag or something, I think.
No, yes,
I
you
did.
just have to escape the opening.
Oh.
Yeah.
Closing bracket.
See, I did put pre-formatted in here, which is why it preserved my indentation and why I didn't have to do break and things. But I didn't realize that pre-formatted would still find a tag inside there.
That was kind of funny. Yeah, that would make putting see code on the internet, really, if you just put it on an HTML page like that.
Well, if you're getting,
Yeah.
well, you just have to escape your carrots.
Yeah.
You guys
Escape your
pro-
carrots and you're good.
You probably just write a regular expression, it'll do it.
Because those are so fun.
Yeah. Oh yeah, so that was the puzzle. Intended to test your ability to trace which thing refers to which other thing when all of them changes. So you can practice this. Next time at Christmas, just assign everybody names, and some of them will be redundant, and some of them will have names that were previously allocated to others, and others will just have different names. And then if you make it through the whole holiday season without forgetting a name, you're set.
I'm done. I suck at names.
Pointer to Bob.
Well, then everybody else will too.
It's like, oh, that's not Bob, that's a pointer to Bob.
Oh yeah, you're right. You gotta have pointers somehow. That breaks it. I don't know how you do it. Pointer. You just designate a cat to be a pointer to somebody. So I put a webcam on its head that feeds back to that person, and then that person is hidden behind the scenes, and it changes who it refers to occasionally.
Just have somebody walk around randomly pointing.
Yeah. Oh, this one. This one's long. You have it in front of you. Okay, I'll keep it here so I can point out specific spots. But yeah, so you have this explore function to write, and explore defines the behavior for exploring. I really should put this on my AI test too. And
Yes, you should.
so you got two different places you can explore, and they're defined by different structures. And so the structures are set up down here in main. And so you got an ogre house and a castle, and they've each got a different set of actions, and then you explore them. Okay, so as far as return values on here, you can have dead, win, or alive. And it says on the instructions here you have to win in each of the scenarios. And if you're alive, you can go ahead and call another function, and if you're dead, you can't. And so you got to be able to make it through both scenarios, calling only functions that result in either alive or win, and eventually calling one that results in win in both cases. Okay, and you notice there's not just one function you can call to do it. In fact, for the ogre, 2 out of the 3 functions result in death. And for the castle, there's actually no way to die in a castle. You can either be alive or you can win. And so the castle is quite safe. But of course, when you're writing explore, you don't know. So the first thing to do here is get the function explore defined. And so we say explore, and we give it a pointer to one of these struct actions. So an explorer doesn't seem to return anything. So you see there's no return value here. So void explore and struct action.
That's twice now.
So the star. Okay, so actions pointer. I'll just call it A. Okay, so there's our beginning of our function here. It's kind of longish. Okay, so in these cases, on ogre house, it's safe to knock, and on the castle, it's safe to knock. And so knock might win just right off the bat, because you win if you knock at the ogre's door. He feeds you soup and tastes like your friend that went exploring the previous week. And
How would you know what your friend tastes like, though?
oh, good point. Maybe you're a fellow ogre. Maybe that's why he serves you soup.
You see your friend's clothes torn up in some corner somewhere.
Yeah.
What was the movie where the sheriff is eating the barbecue? The restaurant, he's like, oh, it's the best barbecue I've ever had.
I do not remember. Okay,
It's an older
good.
movie. Whatever.
Reminds me of an episode of, I think it was Criminal Minds.
Christopher Reeves was in that movie that you're talking about.
Technically,
Yeah.
I can't remember the name.
I can't either. It's definitely a classic, though.
Okay, so I set up here, if knocking leaves you alive,
Yeah.
that means you're in a castle. Because if you're in an ogre house, you would have won right now. So if you're alive after knocking, then you run away, right? That's how you win at the castle.
You serve everybody cooked sheet or something. So I remember that. So I actually realized I just got this one wrong technically.
Did you?
Instead of I used the dot operator instead of the point.
Oh, did I have bright little red arrows in it?
Yeah, you didn't. Oh well.
Oh, I
Did
missed
you
that.
give him full credit?
Well, you did
'Cause
write
I
a red
did that
arrow when
too.
you said makes Kyle's shoes.
Oh, well, that was different.
Yeah.
Oh, maybe I missed that one then.
Didn't miss it on mine.
Got away.
Did he give you full credit? Speed
Yeah,
on that.
as far as I can tell.
Oh, okay, then that's not cool.
Yeah, so I totally missed that. I never had anybody inform me of a grading mistake where I missed a mistake. Usually everybody tells me when I marked one off that wasn't actually a mistake.
Well, then Doc hasn't given you points.
Just give Gus a few points so we'll stop
Yes.
complaining about it.
Yes, please give me points.
Well, he wasn't the only one.
It helps you're missing a parenthesis.
Where? Oh, you're right.
Live.
It's actually that I put an extra one there. But I can't erase because I have a pen. And
You can put another one
luckily,
later.
yes, you can put another one here and it'll be fine. There we go. Okay, so yeah, there you go. That's how Explorer can work, and that's all it takes. That's pretty simple. Okay, so that's the test. Questions, comments, more complaints? You're good at giving complaints on the way through, so that's good. Okay. So to wrap up, I don't really have anything more to say about the test. I think it actually went pretty good. I feel like the median was higher than last time I taught this class, which is good, especially seeing I actually made the test harder. Because that question number 13, the one nobody got with the interrupts, I replaced an easier question with that one. The easier question was something where, I don't remember what it was. And I think I might have changed, I changed a couple others too. I rewrote a few of the multiple choicers. And I think I might have made those harder too. Like the paging one I added, and that was a little bit of a trip up spot. Oh, and I added the privilege level one. That might have been the most commonly missed. And the block device one.
The only thing I remember hearing about this test last semester when I was in software engineering was that people said that somebody said, well, I got like a 77. Mina said, well, that's not bad. I said, no, it's a 77. That's terrible. I remember that, and I think somebody mentioned something about having to use B trees for something. So I kind of thought, oh,
Oh,
sounds
okay.
like it's going to be hard.
I don't think I made anybody use a B tree for anything. I might have. Last time I talked about file systems more than this time. This time I've talked about boot up process like way more than last time. I don't know. It varies. You get the class of the year.
So does that mean you're going to make the final easier?
Final easier?
Yeah, you should make it easier than this test. Just saying.
Well, I think if I made this one harder, I should make that one harder. Like that's the pattern, right?
Or it could go the other way.
Well, I mean, I made one of them harder, so the next one should be harder too. It's a pattern of one item.
Well, shouldn't you give like one easy, one hard? I mean,
Well, things are supposed to get progressively harder. I can't think of any good programming problems could have to do for operating systems yet. Any that could be reasonably completed on a test.
Right. I mean, I have been thinking about the final, and I think I'm going to replace some of the easy questions with like a 20-pointer where you rate a kernel module.
Oh. On paper?
Yeah, on paper. Yeah. I'll test them. Remember I was talking about OCR. I'm going to OCR them and then try and compile them and see if the computer has recognized all the characters.
print K, hello world.
Yeah. Well, it has to print out the hello world when you write the correct string into a file that you created in /proc.
Oh no, that sounds terrible. Don't do that.
Maybe on a gadget that you wrote a device driver for. I'd have to give you the gadget though. You know, I do these paper and pencil tests, but I've only ever given one test in my entire teaching career that wasn't paper and pencil.
You have to actually just look
Not two.
at it and make sure.
But that's it. So maybe we should switch that tradition and have a kernel module writing test or something.
Just present a sort of kernel module problem
Yeah.
based on completion in 1 hour.
Oh, or here you go. I'll give you a half-written B-tree file system like Project 2, and you just have to finish it and make it work.
Actually,
No.
with this
No.
test, I'll kind of just start my question and jump
Just
around.
no.
That's fine.
There could be some good ones.
Wait, do you mean Project 4?
Four is to, this is, what is 4? 4 is like memory management, I think. Did I put topics on anything?
Then I test everything.
Yeah. Just write everything first and then see the rules.
And then you just make more mistakes.
Yeah, Project 4 is probably memory management. It was last time. Oh, is that where you got the Project 4's memory management thing? Or Project 4 thing? I don't know. I thought you knew about what Project 4 was.
Just try this But you said you were talking about project 2, and it sounded more like what we were doing later, so I guessed at project 4.
Okay. Yeah, last time, project 4, I gave out my implementation of the file system, the FAT file system, but I hit a bunch of memory leaks in it, and you had to go find them all.
That sounds like fun.
Yeah, there's a program called Valgrind that will actually analyze your program for memory leaks and give you output and suggestions and stuff about it.
Or you just could plug it into Xcode. Xcode will like flag it in red if there's a memory leak.
Will it?
Yeah.
Okay.
Xcode's really good at that.
That would do it too then. Yeah, it's actually like a 15-minute project with the right tools. But it makes sure that anybody who hasn't found the memory leak detection tools finds them. And then we can all let you be released to be software programmers in industry without any repercussion from our actions.
So what was project 3, 4, and 5 exactly?
3 is kernel programming, like kernel module programming. And that one is set. It will be that. And I need to give it pretty soon here because you're going to be finishing up on Monday and need something else to do. The reason it's stacked way down here is kernel module development has so many ways where it can go wrong. And I'm probably going to slightly shelve the Torah, the Linux kernel, for a little while, like kind of talk about it one day a week and then talk about kernel modules for the other day for a little while. And last time I had everybody write a keylogger, and it only works with PS2 keyboards, the one that everybody wrote. And so I put some PS2 keyboards on some of the machines and made keyloggers. And actually the keylogger, not only that, there's these rules you have to use for passwords, like it has to include some symbols or numbers or uppercase letters or whatnot. And so the keylogger would log the keys, but it would also scan for like pause and few keys, pause, and then it would look to see in those keys if they matched a password rule. Like the password rules, is this a valid password? And if it was a valid password, it would go put it in a list, and you just look at this file that it makes in /proc, and you can see the list of password candidates that have been typed. Yeah, because the password rules, they're kind of uncommon, an uppercase letter, a symbol, a number in a short period piece of text. Yeah, so it's got a very distinct pattern for a keylogger to look for.
Which is also why the best passwords are just long strings of characters.
Well, that's an argument in their favor.
The only problem is that nobody supports you to use a phrase instead of a word.
Right. But if you check your computer every morning for any kind of keylogging activity, then you should be good.
So project 4 was memory management. What was project 5?
Project 5 was an advanced fork bomb last time.
Can we fork bomb my software?
No.
No? Okay.
And you can do it on iSoftware by just running the command, like it's a bunch of parentheses and stuff.
Yeah.
Looking symbols.
Yeah, there's lots of ways. Well, you can write a simple fork bomb in about 3 lines of Python too. But don't do that on a software.
I remember I ran that virus in iSoftware that I made last semester. And it did something really weird to one of the files or something. It created some funny gibberish text as a new file when it wasn't supposed to.
That's right. I remember your virus demonstration. That was a good one.
That was a fun demonstration, actually. I've had a problem with the socket crashing or something whenever I disconnected the client virus.
Yeah.
I still have that thing too. I just don't want to put the code anywhere where anyone can find it because I think Uptime is distributing it and that might be illegal.
The virus
it is a genuinely dangerous thing if somebody actually ran it.
Yeah.
What does it do?
You know what CryptoWalker is?
Yeah.
It essentially was a kind of thing like that where it would it had a server that was running on iSoftware and you'd run the virus file itself and it would take all the files in the directories below it and in the current directory and do the CryptoLocker stuff with it. And of course it would keep itself alive. And all I had to do to unencrypt it was just run the virus again. And sometimes for no reason at all it didn't actually unencrypt the files correctly. I don't know why, so it was kind of dangerous. It was possible you'd lose data forever, so I kind of was very careful with it. I did ask if anybody wanted me to run the virus on their files, and nobody did. I got a copy of their directory or whatever. Nobody offered.
Yeah.
I
That was my
wonder if
Would it run on a Mac?
What's that?
Would it run on a Mac?
It was written in Python. You had to have a certain encryption library installed on Python. I was actually going to write it in C++ or C, so it could actually
Run
on
on any
anywhere.
system?
Yeah.
I bet it would work
That
on
was
Mac with
actually
the
the
right
biggest
Python
problem with my,
library.
Mac file
encryption
system is
stuff
really
in Mac
weird.
OS is that you don't have the right library installed.
It's like
that-
got
or
several
it
layers of
wouldn't install.
sandboxing,
Yeah.
so like those kind of
I know
attacks
it's-
wouldn't really.
Uh,
I don't know. I'd be interested to see. I'd let him try it.
Wanted to have a
If it would, but I don't think it
Place it
would.
on your computer for the.
Okay, well, I'll go ahead and adjourn class, and because today's topic was the test, and we covered that, and I'll see you after I get back next Thursday.
Or something in chat server.
And we'll talk about modules soon.